So in this video, we're going to take a look at how to solve the homework that you had for the Chapter 14 Gases Review for the test. Now, I did not assign all of these problems, but I will be going over the ones that I assigned for tonight's homework. So in the first problem, you'll notice it's just a simple pressure conversion. So make sure as you're studying for the test that you understand all pressure conversions take one step. And so for these, we're going to recall our conversion factors. So for A, we're going to use 27,234 Pascal, and we're trying to convert this to atmospheres. So you're going to set it up using dimensional analysis, and remember that 101,325 Pascal is equal to 1 atmosphere. Also recall that your conversion factors always have unlimited significant figures. So our sig figs in our answer need to match the sig figs in our given, which is 5 sig figs. When you plug that into your calculator, you should have gotten 0.26878 atmospheres. 0.26878 atmospheres. For B, we were converting 729 torr, and we're going to Pascal in this problem, our SI unit of pressure. So we need torr on bottom, so we know that 760 torr is equivalent to 101,325 Pascal. Again, this lets your units cancel, torr with torr, so we're going to multiply the top row and then divide by 760. Again, the conversion factors have unlimited sig figs, so our given is going to determine our sig figs. It has 3 sig figs, so our answer needs 3 sig figs, and when you round your answer to 3 sig figs, you would round it to 97,200. 97,200. All right, I'm going to do C up here. I should have started a little bit higher. I'm going to do C up here. Okay, so we're trying to convert 564 millimeters of mercury, and we're trying to convert that to atmospheres. Again, all these are one-step conversions. We know that 1 atmosphere is equal to 760 millimeters of mercury. So now we're going to get our MMHGs are dividing out. So we're going to divide by 760, rounding your answer to 3 sig figs. You should have gotten 0.742 atmospheres. So those are your pressure conversion practice problems. And remember, for your gas laws, if you're using a gas law like the combined gas law or any of its derivatives, you're going to have to make sure your units cancel. So this is where this is extremely important, that your pressure units cancel when you're plugging into that. And then remember, for the ideal gas law, you have to always convert your pressure to atmospheres. All right, let's look at number 2. Number 2 says, what is the volume of a 5.0 gram sample of carbon disulfide at 276 torr and 80 degrees Celsius? Now, our key word here that lets us know this is an ideal gas law problem is grams. So the first thing I'm going to do is, because I know ideal gas law has moles, so we have to convert grams to moles. So I'm going to do that over here first. 5.0 grams of carbon disulfide, CS2. I'm going to go ahead and convert that to moles, because for the ideal gas law, that has to be in moles. So the molar mass of carbon disulfide, and I'm just going to kind of talk you through that. I'm not going to write it in because I don't have a lot of room here, but you would want to show this if on your quiz, if it was a quiz or a test. You're going to say 12.01 for the carbon, and then 2 times your sulfur atomic mass, which is 32.07. And then that's going to give you, for your carbon disulfide molar mass, 76.15. 76.15 grams per mole. That's your molar mass of the CS2. So that's going to let your grams cancel. And when you divide here, 5 divided by 76.15, that's going to give you the moles of this substance. And so the moles, when you divide, is 0.066 moles. So now we have the moles, and we're going to label our givens. So I'm going to go ahead and write down P, V, N, R, and T. The pressure is 276 torr. Now remember, for pressure in the ideal gas law, it has to be in atmospheres. So I'm going to go ahead and convert that. Again, always show your work for your conversion. These are one-step conversions. We know that 760 torr is equal to 1 atmosphere, and for your pressure in the ideal gas law, you do have to have your units in atmospheres. So that's going to give me 0.363 atmospheres when you plug that into your calculator. So that's in the pressures in atmospheres. The volume here is what we're looking for. So this is our unknown, and so since it's ideal gas law, we know that's going to end up in liters. We just found our moles over here. So we got for the moles when we converted 0.066 moles. We always know R, that's our constant, 0.08206 liter atmosphere per Kelvin mole. And then the temperature is 80 degrees Celsius. Now remember, for all gas laws, you have to convert to Kelvin. So that's true for any gas law. So we're going to add 80 plus 273, and that gives me 353 Kelvin. So now that all of our units are correct, we're going to be able to plug into the ideal gas law. PV equals nRT. Remember to always write your blank formula and then show me how you plugged into it. So the pressure, 0.363. The volume is what you're looking for. The moles is 0.066. The R is 0.08206. And the temperature was 353 Kelvin. Isolate your variable by dividing both sides by 0.363. And that cancels it on this side, and it isolates the volume. Remember, your volume is going to be in liters. So let's plug that into our calculator and see what we get. Now we're going to round this to for proper sig figs. We're going to got 2 sig figs here, 3 sig figs here, and 3 sig figs here. So we need 2 sig figs. Remember, leading zeros never count as sig figs. That's why this has 2 sig figs. So when I plug it in to 2 sig figs, I get 5.3 liters. All right, number 3 says you have a sample of helium with a volume of 175 milliliters at 750 millimeters of mercury. What pressure is needed to reduce the volume? Notice 2 volumes have been mentioned here. Constant temperature to 100 milliliters. So this is one of our gas laws that's related to the combined gas law because it mentions 2 volumes and it mentions 2 pressures. Constant temperature. So let's list our givens. So we have V1 is 175 milliliters. We have P1 is 750 millimeters of mercury. We have P2 that we're trying to solve for, and so since our P1 is in millimeters of mercury, our P2 is also going to be in millimeters of mercury. And then the V2 is 100 milliliters. And be careful because here that has only 1 sig fig. That means this has 1 sig fig, which means our answer is going to have 1 sig fig. Both of your pressures are in millimeters of mercury. Both of your units for volume are milliliters. So since they match, they're going to cancel out. And so we're going to plug into P1 times V1 equals P2 times V2. This is our blank formula. Always write your blank formula. And we're going to plug straight in. So we're going to plug in 750 times 175 equals P2, which is what we're solving for, times 100. Divide both sides by 100. And that cancels it on this side. And that's going to isolate the variable we have here. So P2, your second pressure or your new pressure. My calculator gives me 1312.5, but we just said we need only 1 sig fig. So we're going to round it right here. That means we're going to round it to 1,000 millimeters of mercury. You only need one sig fig, so 1,000 millimeters of mercury is your answer on number 3. Number 4. Number 4 says an unknown gas has a volume of 25 liters at 25 degrees Celsius. At what temperature would this quantity of gas be reduced to 0.5 liters? Again, we have 2 volumes listed and 2 temperatures mentioned. So that means this is not the ideal gas law because it doesn't mention any of our keywords like moles, molar mass, molecules, or grams. So this is one of our gas laws related to the combined gas law. So let's list our givens. We have 25 liters. We're going to call that V1. T1, 25 degrees Celsius. Now remember, you cannot leave your temperatures ever in Celsius. You have to go to Kelvin for all gas laws, no matter the gas law. So that's going to give us 298 Kelvin. T2 is what we're looking for, and it just wants to know what is the new temperature. It doesn't specify that it has to be in any specific temperature, so you can leave it in Kelvin when you're done. You don't have to convert it back to Celsius unless you just want to. But it just wants to know what's the new temperature. And the volume, V2, is 0.5 liters. So both of our volumes are the same unit. They're going to cancel. My T1 is in Kelvin. That means my T2 is going to be in Kelvin. So let's write our blank formula. V1 divided by T1 equals V2 divided by T2. So this is your blank formula. Always write your blank formula. That's going to be a point. If you don't have it, it'll be a point off. If you don't list your givens, that's going to be points off too. You have to list your givens, show your formula, show your plug-in, show your answer, and round to proper sig figs. So let's plug in V1, 25 liters, T1, 298 Kelvin, V2, 0.5 liters, and T2 is what you're looking for. So you're going to isolate your variable, which is in the denominator. So you're going to cross multiply that up, remember. So make sure you watch your algebra. When you cross multiply that up, you get 25 times T2 equals 0.5 times 298. And then to further isolate your variable, divide both sides by 25. And that's going to isolate the T2. And so you end up with 5.96 Kelvin. Now let's look at our sig figs. We have 2 sig figs, 1 sig fig, 3 sig figs. So we're going to round this to 1 sig fig, which means we round it to 6 Kelvin. Number 5, propane gas measures 500 milliliters at negative 25 degrees Celsius and 860 millimeters of mercury. So there's a volume, a temperature, and a pressure. And it says, what is the volume? So that's another volume. That'll be V2 of propane at 5 degrees Celsius and 700 millimeters of mercury. So this is going to be a P1, V1, T1, P2, V2, T2 problem. So let's label all of our givens. So 500 milliliters, that's a volume, so 500 ml. Negative 25 degrees Celsius. Now remember, you cannot leave it in Celsius, so we're going to add 273 to that. Go ahead and show your work for that. And that's going to give you, when you say negative 25 plus 273, that gives you 248 Kelvin. 860 millimeters of mercury, that's our P1, 860 millimeters of mercury. What is the volume? So there's your V2. Since your V1 is in milliliters, that means your V2 is in milliliters. There's no reason to convert it. Now, if you were to convert it to liters in the end, that's fine. I would still grade it and I would count that right, but I'm just trying to do this like the most efficient way, so you don't have to go to liters unless it's the ideal gas law. So it wants to know what is the volume at 5 degrees Celsius. That means 5 degrees Celsius is your new temperature. So let's add 273 to that again, and that's going to give you 278 Kelvin. And then the pressure was 700 millimeters of mercury. Again, with the gas law that's related to the combined gas law, when you have the ones and the twos, your units just have to agree, except temperature does have to be in Kelvin. So this is in millimeters of mercury. This is in millimeters of mercury. That means they're going to cancel. This is in milliliters. This is going to be in milliliters. That's in Kelvin. That's in Kelvin. So all of our units agree. So we're ready to plug into the combined gas law. So there's our blank formula. And let's plug into the formula. P1, 860. V1, 500. Notice that has only one sig fig, and that is significant. That means our final answer is going to have just one sig fig. T1, 248. P2, 700. That also has one sig fig. V2, that's what you're looking for. And then T2, 278 Kelvin. So we're going to isolate our variable. You're going to multiply that up, and you're going to multiply that down. And since I'm running out of room, I'm just going to go ahead and give the solution. So what you're going to end up typing in your calculator is you're going to say 860 times 500 times 278, and then you're going to divide that by 248 and divide it by the 700. We need one sig fig, and that's going to give you 688. So rounding that to one sig fig, you round it to 700 milliliters. Now, for those of you that might have converted that to liters, that's totally fine. If you did convert it to liters, you would have just had 0.7 liters, and that's one sig fig if you have it in liters. That is number 5. All right, let's look at the next problem. The next problem that you had to do for your homework was number 6. Number 6 says, what is the molar mass? Okay, when you see that, that means this is ideal gas law. 9 times out of 10, when you see molar mass, moles, or molecules is going to be an ideal gas law problem. Of an unknown gas that has a mass of 0.75 grams, it occupies a volume of 1 liter, 780 millimeters of mercury, and 30 degrees Celsius. So let's just see what we've got here to see what we can plug into. So we have P, V, N, R, and T. So the pressure is 780 millimeters of mercury. The volume is 1 liter. The temperature is 30 degrees Celsius. And we know we have 0.75 grams of it. We'll use that later since we're looking for molar mass. Remember, molecular weight or molar mass has units of the grams per moles. So what we're going to do, like we've done several examples in class, we're going to find moles using PivNert. And then we're going to take our mass that's given in the problem, and we're going to divide it by the moles that we get with PivNert. Now remember, temperature has to be in Kelvin for all gas laws, so add 273 to that, and that's going to give you your temperature in Kelvin. So 273 plus 30 gives you 303 Kelvin. We always know R is 0.08206. The pressure also has to be in atmospheres, so don't forget to do that conversion. So we're going to do that little pressure conversion. 760 millimeters of mercury is equal to 1 atmosphere. And that gave me for 2 sig figs, because that only has 2 sig figs, 1.0 atmospheres. So now we have atmospheres for our unit of pressure. Volume is in liters. Temperature is in Kelvin. So let's plug it into the ideal gas law. PV equals nRT. So the pressure is 1.0. The volume is 1.0. The N, that's what we're trying to find. The R is 0.08206. And the temperature is 303 Kelvin. So to isolate our variable, we're going to divide both sides by 0.08206 and 303. And that's going to get rid of it on this side, and it will isolate our N, which is our moles. When you plug this in, 1 times 1 divided by 0.08206 divided by 303, that gives me for my moles 0.041. 0.041. So we have our moles. Now we can plug that in here. where I talked about earlier. We were given the grams. We can plug that in to the numerator. So now we're ready to find the molar mass. So I'll say, so the molar mass is going to be equal to 0.75 grams divided by 0.041 moles. Notice now my unit is a unit of molar mass, grams per mole, so divide these two numbers. And that's going to give you, for your molar mass, 18 grams per mole. If you got 19 grams per mole, that would also be acceptable depending on how you rounded your number. But 18 grams per mole is what you need. 18 or 19 would work. We have one more to do, number 8. A chemist collected 8 grams of methane gas at standard conditions. Remember, that means STP, which means it's 1 atmosphere and 0 degrees Celsius. It says, what volume of gas did he collect? All right, so since this is 8 grams, it's going to be an ideal gas law problem. So let's list all of our givens. And let's list everything that we're told in the problem. Standard pressure, 1.00 atmospheres. Standard temperature, 0 degrees Celsius, which is 273 Kelvin. R is 0.08206 liter atmospheres per Kelvin mole. And the volume is what we're looking for. So that's going to be in liters. So I need moles. Well, notice they told me I had how many grams of methane I had. So we're going to be able to convert 8 grams of methane to moles of methane, and then we'll have our moles. So I'm going to do that up here. 8 grams of CH4. We want to go to moles of CH4. Now, the molar mass is going to be carbon 12.01 plus the 4 hydrogens is be 4.04. So that gives you, for the molar mass of the methane, 16.05 grams per mole. So we're dividing by 16.05, and we need 1 sig fig on that. So that's going to round for 1 sig fig to 0.5 moles. So now we have our moles. All right. So now let's plug this into our ideal gas law formula. PV equals nRT. That is your ideal gas law. So let's plug in 1.00 times V equals 0.5 times 0.08206 times 273. Divide by 1, divide by 1, and that isolates your variable. That's going to give you a final volume rounded to 1 sig fig. My calculator, I get 11.2. I'm going to round 11.2 to 1 sig fig, which is going to be 10 liters. So your final answer to 1 sig fig will be 10 liters. Remember, trailing zeros do not count if there is no decimal. So those are all the problems that were assigned for homework. The other problems will be part of your homework tonight.